Have you ever felt like the internet is, well, reading your mind? You know, how it just seems to know exactly what you want to watch or listen to or buy next? Today, we're going to pull back the curtain on one of the most powerful and kind of invisible technologies that's shaping our entire digital world.
So let's just dive right in with a question I think we can all relate to. You finish a song on Spotify and boom, the next one it plays is perfect. It's the exact vibe you were going for. How on earth does it do that? Is it some kind of digital magic? Well, it's not magic. It's actually some of the most elegant and powerful math out there. And the secret ingredient behind it all is something called an embedding. To really get what embeddings are, we first have to understand the huge problem they were designed to solve. And that problem is personalization, but on a massive global scale. And I mean, think about it. This isn't just one or two companies. It's everywhere. Spotify's radio feature, YouTube's Up Next to You, the way Pinterest can find visually similar pins. It even influences the shows Netflix decides to make. And of course, the search results Google gives you. They're all powered by the same basic idea. And this is where data embeddings come into play. You can think of them as a kind of universal translator. Their job is to take our rich, messy, human world and turn it into the clean, logical language that computers can actually work with. And that really gets to the heart of the challenge, right? On one side, you have our world. It's full of abstract ideas, feelings, nuance, and meaning. On the other side, you've got a computer. And at the end of the day, a computer only understands one thing: numbers. It can't get a sad song or appreciate a beautiful painting. It needs numbers. And that is exactly what an embedding is. It's a list of numbers, what's called a vector, that captures the essence, the meaning of something complex. It's the bridge that lets computers understand our world. Probably the easiest way to picture this in your head is to imagine a gigantic, invisible, multi-dimensional map. The technical term for this is a latent space, but map works perfectly. And on this map, every single thing, every word, every song, every picture has a specific location. And the most important rule of the map is super simple. Proximity equals similarity. Things that have similar meanings get plotted right next to each other, they're neighbors. Okay, so take this beautiful line from the poet Langston Hughes. To a computer, that's just a bunch of letters and spaces. But an embedding model can actually translate the deep, complex meaning of this quote into a set of coordinates, placing it on our map right next to other ideas about hope, loss, and dreams. Now, this incredible ability didn't just appear out of nowhere. It's actually the result of decades of work, a long evolution in how we taught machines to understand language. We had to go from just counting words to actually understanding their context. So, way back when, we started with what are called count-based methods. These were pretty simple, really. They basically just tallied up how often words appeared next to each other. But then we had a huge leap forward with prediction-based methods, which got a lot smarter by learning a word's meaning from the other words around it. The old way, using something called one-hot encoding, gave us what's called a sparse vector. You can imagine it like a giant switchboard with millions of switches. A 1 just means a word is present and everything else is a 0. It's fine, but it has zero sense of nuance or any relationship between words. Modern embeddings, on the other hand, create a dense vector. And this isn't just a simple on or off switch. It's a rich, detailed description. Each number in this list represents a different abstract dimension of meaning, which lets it capture all these subtle relationships and context. And you can see this evolution play out over decades. It kind of started with simple stuff like TF-IDF back in the 70s. But the first huge jump was in 2013 with a Google paper on something called Word2Vec. That's when we really started learning meaning from context. Then the whole world changed in 2017 with a legendary paper called Attention is All You Need. It introduced transformers, and that set the stage for models like BERT in 2018, which made this deep understanding of language the new normal. And that brings us right up to today. Seriously, the entire AI boom we're living through right now, from ChatGPT to everything else, is built on the foundation of that transformer architecture. It totally changed how we create and use embeddings. So what was the big breakthrough? Well, it was a mechanism called self-attention. Instead of just looking at a word's immediate neighbors, models could now look at an entire sentence or document and figure out how important every single word is to every other word. That ability to see the whole picture plus the fact you could process it all at once, it was a complete game changer. And models like BERT just perfected this. The name actually tells you how. Bidirectional encoder representations from transformers. The key there is bidirectional. It learns what a word means by looking at the context from both directions, what comes before it and what comes after it, giving it a much, much deeper understanding. So, okay, this is all really cool advanced tech, but it's not just sitting in a research lab somewhere. It is the invisible engine running inside the apps you probably use every single day. For instance, Pinterest uses a system called PinSage to generate an embedding for every single pin to understand its visual style. YouTube's entire recommendation system is basically a two-step process that uses embeddings to find and then rank videos for you. And Twitter, or X, uses them for pretty much everything, finding tweets, suggesting who to follow, even for ads. And the scale we're talking about here is it's staggering. Pinterest alone has to organize and understand the relationships between over 2 billion pins. You can't do that manually. You can't even do it with simple counting. You absolutely need the power of embeddings to work at that scale. So, when you boil it all down, embeddings do more than just translate data for a computer. They create that latent space, that giant invisible map we keep talking about. And it's inside that map that the real magic happens. It's where we can start to see and navigate the relationships between ideas, discovering these incredible, hidden connections that were never explicitly spelled out before. And that leaves us with a final and pretty fascinating question. We've seen how this tech has completely transformed things like recommendations and search. But what happens when we can create an embedding, a meaningful numerical representation for literally everything? Every song, every piece of art, every scientific paper, every single human idea. What new connections, what new discoveries are we going to find then?